now we play the game of where did I put the presentation device in my pocket? Perfect. So yes, I'm Darren Richardson. I'm here to talk to you a little bit about mapping attack surfaces in CI/CD systems. And I feel like I probably warrant more of an introduction because it's unlikely that any of you not from Eficode have ever heard of me. I'm a security nerd. I lived in the United Kingdom for a long time, but it was too cold and grey and dark for me, so I moved to Finland. And if you can see the flaw in this logic, you don't win a prize. I don't know what happened. But yeah, so I have worked for most of my career in cybersecurity, kind of accidentally, in that I knew about security and people kept asking me questions and all of a sudden it was my job. So I've worked in very small startups of hyper-technical focused people in AI applications, and I've worked with larger companies consulting for other larger companies in the most generic infrastructure you can think of. So I've had to think of security in a lot of different ways. A little bit of personal stuff about me. I have too much beard and I play the guitar. If you want to talk to me about either of those things, feel free. If you want to talk to me about any of the security stuff or anything in general, I am not as scary as I look. I want to specify that now. I do look angry all of the time. My face is just like this. Please come and talk to me. So before I can talk about mapping attack surfaces in CI/CD, I have to explain what CI/CD is because I work for Eficode and they are a DevOps company, and obviously I know what it is. I'm sure some of the consultants from Eficode will disagree on that later because of how I mark these things, but they're the professionals. I'm just a security nerd. But here is my summary of what CI/CD is in 100 words or less. And I say my summary, I actually mean ChatGPT's summary, because frankly, 80% of my job, at least the, let's say the documentation tasks, have been replaced by ChatGPT, which has given me a lot of free time to actually work on the things I enjoy, which is nice. But CI/CD, I want to simplify from this. CI/CD is a way of putting things in places. Like, this is a huge simplification. But CI/CD is what exists between your coders and the places they're putting code. And what we're wanting to map is the attack surface of everything that exists between. So we can break it down into two elements: CI, automated testing, frequent integration, this kind of thing, and CD, which is the delivery, which is automatic deployment, staging environments, pipelines. Basically, it's a pipeline where your developers stand at the top, they pour code in, and deployed systems come out the bottom. That's how I simplify it, at least. And then we need to address what is an attack surface, because, well, it's a weird term. So an attack surface is, again, ChatGPT's summary there if you wish to read it. An attack surface is everything that occurs. We can kind of break it down. I have a metaphor in my head, which is the house metaphor. Think of your house. If you have a house, maybe you have a garden, you have a wall, maybe a fence, you have a front door, you have windows, you maybe have a basement, maybe a ladder from the basement up into the main house. This is your attack surface. This is where people can get in. And this is what we're thinking about when we're talking about attack surface mapping. We want to determine where people are able to move and interact with your system. So we have like a number of different types of attack surface. We can think network attack surface. This is your open ports, your network protocols. You can have application attack surface. This is your applications as you build them and any vulnerabilities within them. So there are a long list of attack surfaces. We can talk about operating systems, where we're talking about the actual OS your systems are installed on. All this makes up your attack surface. And there's kind of a terminology thing I want to discuss. People quite often use attack surfaces and threat models synonymously. There are people who will use them as completely different things. A threat model is a process by which you examine the ways your system might be under threat, and it should contain an attack surface map. If you meet someone who is telling you there is a distinct difference between a threat model and an attack surface map, they are trying to sell you both. They are trying to give you both of those processes. So just be aware, terminology, there isn't a whole lot of difference. One just contains the other. It's like, CI/CD is part of DevOps. Attack surface mapping is part of a threat model. So if you know threat modeling, a lot of this might be familiar to you, and I won't hold it against you if you leave. And if you take everything we've discussed about attack surfaces, about your house, about the fence, about the building itself, about the lock on the door, about the windows and how you might look at those things, you will understand the onion of security. Now, its technical name is defense in depth, but I think the onion of security is a lot more snappy. So this is the thing about security. You've probably all heard the joke that security is like an onion, in that you keep peeling back layers after layers and find exactly the same thing, and then you start to cry. And that's how security works. So unfortunately, that's how security is seen. And I kind of hate myself for standing here and painting this picture of it, because I'm like a proponent of security not being as negative as everyone makes it out. So I want to tell you a story about this threat model here. I used to work in a AI company, startup. I was the 17th employee, and I was hired to do security things. And we worked with AI systems for autonomous navigation in vessels, like to imagine Tesla Autodrive, but for ships. That's what we were building. And in a attack surface mapping exercise, 5 o'clock in the evening, we were all tired, and one of the people stopped dead in the middle of this sentence and said, "We're talking about ships. Do we need to discuss pirates?" And at that point, the conversation derailed, and yes, we spent the next 4 hours discussing pirates. The coffee was put away, the Jalovina, the Finnish booze, was brought out, and we sat there drinking and discussing piracy to try and make ourselves experts in it so that we could include it in our attack surface map. And that's what I mean when attack surfaces can involve everything. We had to take a break so that we could become experts in piracy. It's good fun. You can find fun in security if you look for it. Now, I'd like to show an example here of a CI/CD system, and it's going to be too simple to be functional, but it displays what I want you to see, which is code comes in, code is processed, artifacts are pushed out, these go to various testing, staging, production environments. This is the essence of super simplified CI/CD, as I see it as a security professional. If you talk to a DevOps expert, they will tell me to remove this slide because it doesn't represent CI/CD at all. But this is the basic building block. And we are going to move on from here because it's bad. It's a bad summary. I can't say it's a good summary. It's just clear visualization. So we're going to move to examples which are too complex to be easily understood. Here we have more realistic CI/CD. Can you see now why I didn't start with this? If I start with this slide here, people start to wonder if they can even follow it. It's actually not complicated. It's just, it has a lot of steps. And this is what a CI/CD system looks like. So we have exactly what we have in the first one. We have storage of code up here, pipelines, storage of built code here. It's exactly the same system, we've just opened it up a little bit. And we will continue to open it up because now we know what CI/CD is, we know what threat modeling is, we know what an attack surface is. So let's get started. From this, we need to apply the idea of defense in depth. We need to consider everything from our onion in this picture, which means we need to start considering everything. We'll get to that a bit later. From this picture, I would say we have 4 things, and what we're looking for here is we're looking for where data. So if we take a system off the internet, unplug it, leave it for 2 years, plug it back in, nothing will have happened with the data, assuming it's stored correctly and such. We are looking for where data is created, we're looking for where data is moved, we're looking for where data is manipulated and where data is accessed. These are the core components of mapping an attack surface. These are the components which we can look at and see, okay, here is where we need more scrutiny. Here is where we need to look in order to get an accurate view of the attack surface. Now, I would like everyone to take 30 seconds and look at this and just think of where you might see an issue. Just think about it. I will go on and talk about 4 issues here. It's not the only 4 there are, but I've been given a 40-minute time slot and I can't talk beyond that. So take a look, see if you can find 4 places where you would look here. And if you can, that's the core of attack surface mapping. Don't worry, it's not a trick question. It's not. I don't have like a hidden zone down here where I'm going to put all my actual things. But I'm going to start moving on by taking a closer look at Git. This is the first one. This is the first major area of concern because this is where everything starts. Everything goes into Git. We have 2 nodes here in Git. We have custom code and open source code. What we're looking at is whether or not we are building something. We clearly are. Whether or not we are bringing something in. We clearly are. So we have 2 different parts of an attack surface here. We have external components being brought in, and we have custom components being made. And this opens up so much of the onion that we need to consider at least the top 4 layers of it, things like procedures, applications, tools. Now, obviously, if we're looking at custom code, there are a lot of potential pitfalls there. The OWASP top 10 is the... I have to say, the OWASP top 10 vulnerabilities bothers me in that people use it as a standard for security. They say, if I'm doing things according to the OWASP top 10, I'm doing things securely. And I disagree. If you are doing things according to the OWASP top 10, you have started to do things securely. The top 10 is the top 10 for a reason. They're the most common issues. There's only 10 of them. They limit themselves specifically by what they're releasing. So in Git, what we're going to do to look at the attack surface, we're going to think of things like accidentally malicious code, people leaving in things like injection vulnerabilities, people leaving in any kind of issue that might allow access. We can look at the OWASP top 10, but what we're looking at here is people creating something which is not up to the standard it needs to be. And we also have to consider the release process, because not everything that goes into Git is coding. Coding is a part of it. Then there are peer reviews. People need to be able to look at the code and understand the code and say, okay, this is good, this is bad. We need to insert security tooling there to catch parts of the code with, static testing, this kind of thing. So when we're looking at a Git surface, we're looking at human elements, we're looking at technical elements, and then we're looking at open source external elements, because open source elements, external elements, things you can't fully control, are a growing section of attack surface. They are expanding, they are getting much larger. We are seeing many more of these attacks than we once were. They are things like typo squatting are incredibly easy, and they're one typo away from getting into your code. So if we look at the results, top 10 vulnerabilities, any other vulnerabilities, malicious code insertions, and open source dangers are just 4 of the things we see from Git alone when mapping the Git attack surface. And that is just Git. Pipelines. Okay. To level with you, pipelines are an extremely complex subject for a security professional. If you come to me and explain the function of a pipeline system, my initial response is, that sounds like a remote code execution vulnerability, let's patch it. And then you tell me, no, that's actually what you want the system to do. You want to be able to execute arbitrary code on a remote server as its entire function. This is difficult for me to parse because this is exactly what I've been taught is bad. So we have kind of a back and forth between DevOps and security in that pipelines are just formalized remote code execution. That's all they are. And we have to look at them from that perspective. Now, if you've never used a pipeline system before, something like Jenkins, something like GoCD, or anything built into Git, GitLab, GitHub, you probably know this, but I'm going to explain it just briefly anyway. A pipeline system basically takes a set of instructions in a typically YAML file and runs through those instructions. They execute sequentially and do what they're told. This opens up the path to something called poison pipeline execution. And poison pipeline execution is where you inject malicious code, not into the code base itself, but into the build system. The build system has the opportunity then to run the code, to execute these vulnerabilities, to insert things into your build system without leaving a trace in the source code itself, and make it to your end storage because that's where your pipelines are pushing things anyway. And can I just ask, show of hands, even though it's quite difficult to see with this light shining in my eyes, show of hands, how many of you have heard of poison pipeline execution? That's maybe a quarter of you. This is, well, let's approach it from a different angle. Does anyone remember the SolarWinds hack? Raise a show of hands. That was poison pipeline execution. That was code being added to the Orion system in the build process without access to the source code. As far as I understand, I'm not an expert on the situation, so if you want to correct me, feel free to do it at the end. So poison pipeline execution is something that is dangerous, difficult to detect, and practically no one is talking about it. And I actually planned to come up here and be a bit annoyed and outraged about the fact that no one's talking about it, but then I remembered I'm the security professional in DevOps. I'm the person who should be talking about it. So here I am talking to you about poison pipeline execution. And how this works, basically, you can do so many things if you can alter that YAML file. One of the things you can do is have it ping any credentials it's using to an external server, because why not? It's a simple curl. Curl the environmental variable to a server you have waiting, because you can't do something like print the variable. Most pipeline systems are smart enough to know that. But if you curl it to an external server you have waiting, it will happily send it in plain text because it has to. And that's kind of a problem. It's, again, why we have lots of talks on zero trust architecture. I have 30 minutes left, 20 minutes of which is for the talk and 10 is for the questions, so I'm not getting into zero trust right now. That is a longer topic and a very interesting one, but not one I'm going to talk about at this point. But getting the credentials is not the only thing you can do inside pipelines. You can basically have it do whatever the pipeline has permissions to do. And it usually has permissions to do quite a lot because it's building your software. So this is a huge part of attack surfaces in CI/CD. And well, frankly, it's not getting as much attention as it should. But there are other issues here. I've talked about poison pipeline execution, but I also want to talk about PBAC, pipeline-based access control, which is exactly the same as RBAC. It's exactly the same as any kind of access control in that if you don't configure it properly, it will go bad. And I also want to talk about the insufficient credential hygiene, which is exactly what we're talking about in PPE. I don't know how many people work with pipelines, but I wonder how many have encountered a plain text password in a YAML file just in the source code. How many of you have run something like GitLeaks through your Git source repository and found out how many secrets you actually have hidden there? I'm guessing quite a few of you have done it, and I'm guessing quite a few of you have been slightly disappointed in your findings. I will honestly say I have, because I'm terrible at this. It's why people don't let me code anymore. So another thing I want to talk about here is ungoverned use of third-party software, because I've talked about it before. I'm not going to make too large a point of it here, but if your pipeline systems can access the internet and download anything they want, then your pipeline systems can download anything they want. This is a terrible way to have it set up. They can get literally anything, and they will, because it's easy. So this is why we talk about this in the attack surface. This is something that has to be restricted. External dependencies. I've talked about this a lot. I'm going to talk about it again because it keeps happening. It warrants talking about. And because it allows me to talk about a term in cybersecurity that has annoyed me for a while. We talk about the idea of a Trojan based on the Greek mythology of the Trojan horse, that at the end of a 10-year war, the Trojans saw a giant horse outside of their gates, conveniently large enough to fit 100 soldiers in full battle gear, and they just casually brought it inside their own city. This is an unfair representation of the Trojans we see today, which are sophisticated, they are clever, they are subtle, and they do not rely on stupidity. They rely on things like exhaustion, decision fatigue. So we talk about Trojans. I don't like to, because I think it's kind of insulting that we say that people who get affected by these things are similar to the Trojans who made a very clear mistake of casually bringing 100 soldiers into their city. This is not what Trojans are. But this is what's happening with external dependencies. And there are two key things I want to talk about here that you need to consider when attack surface mapping. And these are your dependencies. Well, it's only your dependencies, but there are two things here. Dependency confusion, typo squatting. If you're coding, it's something in Python, you're using Django, maybe making a REST API, you miss the D at the start of the package, all of a sudden you have malicious code. You are one letter away from malicious code. That is how far away malicious code is at any given point. And the second one is, of course, dependency hijacking, in which point you aren't a letter away. The dependency has just been taken control of by someone else. And these things are why, well, first I want to talk about mitigating these things, because the idea is we could easily put the dependencies inside any kind of local storage and only get dependencies we know are trusted. And that is the best way to do these things. And I think if a lot of DevOps professionals put their hand on their heart, they will say they don't do it like this, and they pull containers from the internet. And this is a bad idea. So, I'm not going to dwell on external dependencies too much more. Yeah, let's move on from these. I think I've made the point on them by now. So, storage is, in my opinion, one of the last places we need to look here. We've looked at Git, we've looked at the pipelines, we've looked at the external dependencies, but artifact storage is quite an interesting one, because everything that ends up in storage is viewed, in my opinion, as trusted. And a lot of people will use tools. For example, in Artifactory, you'll have checksums to ensure that everything is there that is supposed to be there and is trusted. If you ignore these things, which a lot of people do, what happens is maybe someone's just trying to push a new version of a container to Artifactory, so like an image, so they can use it in their next build. They don't follow the procedures. They don't have a pipeline to bring them in. They push it themselves. They don't bother doing the checksum stuff because they know it's fine. It's absolutely fine. And maybe at the time of writing, it is absolutely fine. But just because something is fine when you do it, it doesn't remain that way. And once you introduce that kind of weakness, that kind of flaw, it doesn't have to affect you right away. And this is where I want to take a brief diversion and talk about timelines in cybersecurity. Any problem you have is not a problem today. You will run into problems down the line. I think the average discovery time for cybersecurity issues is 3 months. That's quite a long time. 3 months of damage that can be done. And that's the average. Lots of them are longer. If you have something like this where you're disabling checksums, this is not going to bite you immediately. This is going to bite you a year down the line. So what we have here in the storage is kind of the primary goal, in my opinion, of targets when it comes to CID systems, because, well, this is where things are being pushed to staging, to production. This is how you get code out to people. This is the last stage. This is where all the checks are done, where everything is completed and you are ready to shift. So if you can get things to storage, people aren't going to look at them again. Like, people aren't going to open the crates to see what's being shipped when they're already on the truck. So this is the mapped attack surface. 4 things. It's by all means not all of them. Obviously, production is its own attack surface. There's going to be security tooling in the pipelines. This is kind of the core of what I'm trying to say. But the astute among you will know that I am still 11 minutes from finishing my talk, which obviously means either I'm very bad at planning time or I'm not done. So let's talk about the rest. Because so far all we've talked about is CI/CD attack surface mapping, which is exactly what I'm here to talk about. Congratulations, we have reached the end of that. Now we have to acknowledge that everything is still built on infrastructure. There is no way of separating CI/CD systems from the infrastructure on which they are built. You still have Git as a source of version control. It is on an Ubuntu server hosted on site. You know where this is. You can go and put your hand on it. This is a known quantity. You might have pipelines. These may be virtualized Debian servers. Can't put your hand on those. They're in Google Cloud. And then you have a Kubernetes cluster running your build actions. Okay. So we have these 3 things, and then you have an artifact storage, and no one's actually quite sure where it is. You have a testing system, which is actually just one of your developers' laptops. You have a staging system in your documentation that is not actually reflected in reality. And then you have production, which is actually where most of your bugs are found, where most testing occurs. These are all things we have to consider. And you're probably asking, do I have to be an expert in server infrastructure, in cloud security, in Kubernetes security? And I have a sad answer for you. Yes, I'm afraid you do. I'm afraid if you want to do attack surface mapping at CI/CD level, what you need to do is be aware of the entire technology stack upon which it is built. And obviously you don't want to do this yourself. You'll have a team surrounding you and it will be fun and people responsible for other things. But if you go to the trouble of securing your CI/CD infrastructure and you don't secure the underlying architecture, all that is going to happen is the attacks will come at your architecture. Think about it like our house metaphor. You've built a house, you've replaced your wall with a 6-foot fence. You know people are not going to get over that unless they're particularly interested. So you replace the lock on your front door. You spend thousands of euros on the best lock you can find, but your front door is not reinforced. All you've done is you've shifted the attack surface from the lock, which may have been pickable and is now not, to breaching the door itself. So yes, I'm afraid you do need at least some understanding of these things at a security level. Otherwise, your attack surface map is incomplete. And that is a problem because these are each of these technologies is extremely extensive. The security of Kubernetes, for example, is another topic I could happily do an hour on. Cloud security, it's another hour. So what I'm trying to say here is kind of a commentary on the security industry itself, cybersecurity. I personally have always found myself to be a sole security developer. People have brought in one person and expected that person to do security properly. That is not possible. If you are dealing with all of these technologies, you can't expect one person to be an expert in server security, an expert in cloud security, an expert in Kubernetes security. So if you find yourself mapping attack surfaces or doing any security task, don't go it alone. It's a poor choice. It is not your sole responsibility. I don't even know how many of you are in security, but I know the patterns as I have seen them. It is not a single person's responsibility. If you're an expert in all of these, fantastic. Enjoy the vast amount of money you'll be able to make from the jobs you will be offered for being an expert in all of these things. I am not one of these people. So make sure you build security teams. Make sure you use security champions. Sorry, I'm going off on a bit of a tangent here, but it's been bothering me for several years, so now you have to suffer through it. I apologize. But yes, just think about these things, because if you put the responsibility of security onto a single person, you're going to fuck up. I'm sorry, but that's how it's going to be. And security incidents kill companies quicker than anything else I've been able to find. Bankruptcy is a slow process. Any kind of HR scandals are slow processes. Questionable business practices are slow processes. Nestle, I'm pretty sure, are still using slave labor to produce chocolate, and they exist as a company. None of these things will kill a company faster than cybersecurity incidents. In Finland, we had Vastaamo, the psychotherapy unit, who had a data breach because they were ignoring security, and they now no longer exist. I think the whole thing took a month to kill that company. I think here in Denmark, not too long ago, you had a cloud service provider who casually said, sorry, we've lost everything and our backups don't work. That is not a position you want to be finding yourself in, because companies can come back from so much. And sometimes cybersecurity incidents are one of those things, sometimes. And it's easy to draw a delineation. This is again a bit of a tangent, but I just want to mention it. Data breaches are personal things. They are like SolarWinds. We talked about the SolarWinds hack. Nothing really happened to SolarWinds in my understanding. They continue to operate. They continue to work exactly as they have been. These smaller companies who had data breaches don't. They cease to exist. And it's much easier to abstract out a security failing when it does not hit anyone personally. But when you're dealing with personal data, people who are on the receiving end of this attack will feel closer to the attack themselves. And we have all these considerations like GDPR, HIPAA to guide us when working with these kinds of data, but it's just worth remembering that these are people. And if something happens to the data you have regarding these people, they will be the ones who feel attacked. And that's a good way to consider security from the end user point of view and make sure all consideration is taken to securing that data. I want to take 1 minute to talk about the real threat. 88% of attacks are instituted by user error. That means as a technical security person, I spend 40 hours a week dealing with 12% of a problem. I'm looking at it from a technical point of view. We do an annual security training. I'm sure most companies do an annual security training. Everyone needs to take more responsibility for cybersecurity because this is the real problem. This is 88% of the problem, and it receives so little of the attention. Phishing, social engineering are still the prevalent attack routes. No one is exploiting you. No one is using APTs against you. These kind of technical issues are so, they're just rare. They are 12% of the problem. So I want to give you some advice, things I've been saying. Talk to people. Security has to be an open conversation, and it's so easy as a security professional to move out of the company itself and become a silo all by yourself. You can just be the person who sits in the corner and says no when anyone tries to do anything. Don't do that. Get involved with everyone. Connect with everyone. Build a team of enthusiasts. There are so many people interested in security. Build around them, get them involved, and use them to push like a method of saying yes and not a reason to say no. This is how we mitigate the 88% of the problem. This is how we talk to people. This is how we communicate with people. And it doesn't matter if it's servers, if it's online systems, or if it's CI/CD. This is the real problem. And this is what we should be doing far more work to address. And I do have a brief word to say about what I think the future is going to look like, which actually looks a lot like the original simplified view, in that we have a contained ecosystem. GitLab are already doing something like this, where everything is built in, security tooling built in, invisible, until it spots a problem. This is what the future of CI/CD systems is going to look like, in my opinion, where everything is invisible, storage is built in, everything is self-contained, and what this does to your attack surface is it limits it to a single entity. It's no longer 7 entities spread across a cloud system. It is one single self-contained ecosystem. And this is going to be honestly one of the last chances I get to do this talk, because over the next few years, I feel like this is what CI/CD systems are going to look like. And if I try and just do this talk again, it will be, here is one system. It's called GitLab, it's called GitHub, it's whatever you're using. It's a single point of entry attack surface. 3-minute talk. Now I'm done. Great. So this is not going to solve all the problems. It will solve a lot of the problems of mapping the attack surface, but production will still be where you find all your bugs. Staging still may or may not exist, despite what's said in documentation. And the testing will still just be run on someone's laptop, because you can't mitigate users. Thank you.